Okay, so let's start talking about it.
We just started.
Just started.
Come on now.
It's been 6 minutes.
Come on, Caleb.
We should know something. What do we know? Any of these that we should know pretty well.
Natural, whole.
Okay, what are the natural numbers?
1, 2, 3.
Okay. Now, one thing to keep in mind when we're showing a set of numbers, notice how we're talking about set notation in a second. Does anyone remember what kind of grouping symbol we use for set notation?
Element.
We do use the element symbol at some point.
Curly.
Set of
Curly thingy.
Curly
brackets.
Curly.
brackets, right? So the natural numbers, I open it up. Hey, Alan.
Oh, sorry.
Thank you, sir. I open it with a curly bracket, and the first natural number is what?
1.
1, and it goes 2, 3, 4, and then it just keeps going. Right? There's my natural numbers. The reason why they're called natural numbers, and I mentioned this before, they're also called counting numbers because they're where you naturally start counting things. If you have something, you have one of them. If you have a second, you have 2. If you have a third, you have 3, right? So they're the natural numbers that are where you naturally start counting. The whole numbers, what do we know about those?
That's the real numbers, starting at 0. Going
So one thing I want to point out is all of these numbers, you see how real numbers is up here at the top?
up.
Everything here is a real number. Everything that is within this is the real numbers. But the real numbers also, that means that they include a lot more than just the natural or just the whole. But what were you going to say? The whole numbers start with what?
0.
0. Whole numbers do start with 0. Again, curly bracket to open it up. 0, 1, 2, 3, 4, so on. One thing I do want you to notice is, do you see how the natural numbers are completely within the whole numbers? See how the natural numbers circle or ovals inside of the whole numbers? Okay? That is literally because the natural numbers are a type of whole number. Every natural number that exists is also a whole number. It is inside of that grouping of whole numbers. Does that make sense? We good with that detail? Yes? Okay. So what do I mean by integers?
-3, 2, 1, 0, 2.
Are those the only integers? No?
Go further down or further up.
Okay, so we can go further down or further to the left, and we can go further to the right. So what should I probably put here to indicate that I can keep going in each direction?
Dots.
Ellipses, yeah. Okay? So don't forget the ellipses are indicating that it keeps going. Notice how the integers are the first number set that have negatives. But, do you see how the integers also include the natural numbers and the whole numbers? Again, that is why the whole numbers and the natural numbers are inside of that integer set. We good there? Yeah? Okay. Caroline, you good with that? Donovan? Alright. So what do we mean by rationals? This is usually where students first get stumped a little bit.
Fractions.
Okay? They are heavily connected with fractions. Look at the first half of the word rational. It is a ratio. A rational number is a ratio of integers. Okay? Anytime we're dealing with a rational number, it means that we're dealing with a ratio of integers. Okay? Notice I am not able to list these because there's a lot of them and a lot of variations of them. Can anyone give me an example, though, of what a rational number might be? let's work on that mathematical language.
That's right.
When McKay says over, what does he really mean?
2 divided by 2.
2 divided by 2, right? Is that a ratio of integers? Yeah. And it simplifies to 1. That'd be a rate, but that also means, I want you to know this because it's actually pretty important, that's a ratio of integers. So 1, which is a ratio of integers, isn't that also a natural number? Isn't that also a whole number and also an integer? So every integer is also a,
Ratio of integers.
right, -2. Isn't that the same thing as -4 divided by 2 or to 2? So every integer is a rational number, every whole number is a rational number, every natural number is a rational number. However, most of the time when we think about rational numbers, we don't think of them as 2 halves or 1. Come on, what are some other ratios of integers that we might think of? Donovan, give me one ratio of integers, a rational number.
1 ratio?
Say again?
You said 1 ratio?
Yeah, just give me one ratio, a rational number, a ratio of integers.
1 to 4?
Okay, 1 to 4. That's a good rational number. Jeffrey, give me another ratio of integers. Say again? Work on that language, not 1 over 2, 1.
Divided by 2.
There we go. Right, divided by 2, that's a good one. Zay, give me another one. I'll take Caroline's, I'm going to come back to Zay.
Yeah, go to Carolina.
Caroline, what was yours?
1 divided by 3.
1 divided by 3. Zay?
2 divided by 4.
2 divided by 4?
Yeah, 2 over 4.
Okay, I'm going to, well, 2 what?
2 over 4.
Not over. Work on that mathematical language.
2 4?
You can say 2/4, or what does this fraction bar mean? What mathematical operation is that? Divided by. You originally said that right, but then you switched it to 2 over 4. Now, we'll point this out. Isn't 2 divided by 4 the same thing as 1/2?
Yep.
Okay, so give me something that's different than 1/2.
4/5.
4/5, there we go. Alan, give me one more.
Stay around. 2/3?
2/3. All right. Does anyone have any others they want to give us? Or can we keep go from here?
11 over
11 fifths?
5. 11 fifths.
Or 11 divided by 5?
Yep.
Got a more fun one. Let's do 5 divided by 11. I like 11 fifths. I'll keep that as well. But let's do 5 elevenths as well. Okay. I do actually like 11 fifths for a couple reasons. One detail that I want to make sure you clearly understand, and I want you to write a note of this to yourself at some point within this, is 1 divided by 4. What is that as a fraction?
1 to 4?
Sorry, as a decimal.
1, 2, 5.
1 to 5?
So 0.25. What about 4 divided by 5?
1 to 8?
0.8. What about 1 divided by 2?
25.
So 0.5. Okay. What about 11 fifths?
2.2.
All these decimals have something in common. Do you know what it is?
They got a point here.
They're decimals, yes. Does that decimal keep going or does it stop?
They keep.
They stop.
I mean, technically there are zeros afterwards, but do I need to write anything else out?
No.
So that decimal has stopped. Do you know what we call that in mathematics? Starts with a T. It's a famous Arnold Schwarzenegger movie where he's going to end someone. Say again?
Terminator.
The Terminator, right? If the decimal stops,
What time is
it terminates. Hey, you've heard that term before with rational numbers, right? Okay. So notice here, right, this is not part of that real number, it's just indicating with this, the decimal terminates. Okay, what about 2/3? Does anyone know what that is as a decimal? Hmm?
Wait, never mind.
Well, let's do 1/3 first. What is 1/3?
Ain't it like 33.3?
175.
It'd be 33.3%, but it's not even quite that, huh?
175.
So, let's look at this. Don't forget, this is important. What is this symbol? Divided by. So I'm dividing 3 into 1, right? Obviously 3 can't go into 1, but how many times can 3 go into 10? 3 times, right? So I get 3 times 3 is 9, subtract that out, get a 1. Bring down that 0. How many times 3 go into 10?
3 times.
3 times 3 is 9, subtract it out, I get a 1. Yeah, is that 3 ever going to stop?
No.
So it's not 33.3, it's 0.33333 forever and ever and ever. Say again?
3 repeating.
3 repeating, yep, 0.3 repeating.
The line over.
There we go. Alright, 2/3. Now I want you to notice, aren't we just doubling 1/3? So if I double 0.3 repeating, what am I going to get?
26 repeating.
0.6 repeating. Five elevenths. You check it out. So it means 0.45 repeating, where that 4, 5 repeats. So 0.45, 45, 45, 45, 45, 45, forever and ever and ever. So what do all these have in common? What does the decimal do?
Repeating.
Okay. Anytime you are dealing with a ratio of integers, a fraction, that decimal could the decimal version of it will either terminate or it'll repeat. That's a definition you've probably heard in the past. That for a rational number, the decimal either repeats or the decimal terminates. Make sure you have that note down, right? Natural numbers, whole numbers, integers, those are easy to define just by showing a list of things. But a rational number is a little bit harder. We need to know it's a ratio of integers in a fractional form, but in a decimal form, that decimal either terminates or that decimal repeats. You might get some free time to do some fun things with decimals, or with fractions and decimals, which I know you wouldn't think that, but there's some interesting things that happen with decimals and fractions. I know you think I'm crazy. Just listen out. You think I'm crazy? Let me ask you all this. 0.9 repeating. Is that equal to 1?
Yes.
Yeah,
Why?
because you rounded.
But that's rounding.
So it's,
Sam-
you still got to round it up.
But can you just round stuff? I'm not saying is it close to 1, I'm saying is it the same thing as 1?
No.
No.
No?
No.
Okay, so what about 1/9? Does anyone happen to know what 1/9 is? We got some calculators out there. Type 1 divided by 9, get the decimal version of it.
0.1111.
Okay, that
0.1 repeat.
0.1 repeating?
Yeah.
Okay, so then what would 2/9 be?
2 repeating.
0.2 repeating?
Yeah.
3 repeating.
So 3/9 would be 0.3 repeating?
Yeah.
So then what would 9/9 be?
1 repeating.
No?
One. It just be one. Just one.
Oh.
But if you use this pattern, I mean, what would 8/9 be?
8 repeating.
So 8/9 is 0.8 repeating, isn't it?
No, they're gonna turn to 9. They're gonna turn to 9. It's a 9 in decimal.
Huh?
It's a 9 in,
What do you mean?
it ain't.
Oh, well, your calculator's rounding. It's not going to, because your calculator can't spit out exactly 0.8 repeating for forever and ever and ever. Your calculator's going to round, but that's not exactly what it is. 8/9 is 0.8 repeating. We saw here that 1/9 is 0.1 repeating, right? 2/9, 0.2 repeating.
3/9 equals to 1/3.
It does, which isn't 1/3, 0.3 repeating. So 8/9 would be 0.8 repeating, so 9/9 would be,
1.
I mean, we know it's 1, but wouldn't it also be 0.9 repeating?
Yeah.
So is 0.9 repeating the same thing as 1?
Yes.
Yeah. Right? There's actually interesting patterns to find if you're willing to look at them, but that's just one small one. What else was I saying? Oh, irrational numbers. First off, do we have any questions about rational numbers before we move on? We good? Okay. Irrational numbers.
Square roots.
Okay, a lot of square roots. Give me an example of a square root that would fit under irrational.
Square root of 5.
Square root of 5. That would be irrational. What else?
Square root of 7.
What did you say, Canty?
Square root of 50.
Square root of 50. Square root of 7.
2.71828.
Yes. Just trying to figure out where you're going with that. Does anyone know what number that is?
You can put E.
It is the number E, Euler's number.
105.
That's an irrational number. Does anyone know another irrational number that we use a letter to represent?
5.
Pi.
3, 5,
What's the letter?
Say that one more time.
I've never seen it. What is that letter?
Pi.
Yeah.
It's a Greek letter.
You've never,
Pi is a Greek letter. You've seen pi in math class, right?
Yeah, I didn't know it was Greek.
You just didn't know it was a letter, is what you were saying.
Yeah, I thought it was the same.
Ask all the way up, please. Yeah, that is a letter. Let me ask you this then. What about the square root of 16? Would that be an irrational number?
No.
no,
Why not?
4 times 4.
Okay, so the square root of 16 is 4, which makes it actually a natural number,
Yeah.
which is also a whole number, which is also an integer, which is also a rational number. So we want to notice that it's those imperfect squares. There are some other special irrational numbers out there. And so here's the last thing I want to say. If you put together all of the irrational numbers with all of the rational numbers, you're going to get every single decimal that could ever exist. What number set do you have when you have every decimal all mixed together? Every single number that could ever exist?
Real.
The real number system. Hey Caroline, please keep that mask up. Donovan, same deal. Donovan, there you go. So the idea is that the real number system encompasses everything from the rational numbers, everything from the irrational numbers. Which is why if we're dealing with a continuous function that contains everything, what number system are we dealing with?
Real.
The reals. Right? If you're dealing with a continuous number system, you're dealing with the real number system. If you're dealing with a discrete model, you're usually dealing with the natural numbers, maybe the integers. Are we good with this? We got notes on the number system, so we can refer back to this and know what number systems we're dealing with in the future, right? Ooh, I forgot. What's the symbol for natural numbers?
For natural,
Mm-hmm.
the 2, 2 lined in.
Okay. It's called blackboard bold in. Which you won't always see me write that blackboard bold every time because it's really hard for me to do it with W or for whole. But yeah, it's called blackboard bold.
What about for Q too?
Q, if I remember correctly, isn't that bad. It's here, I think. I'd have to go back and study it.
Yeah, that's right.
Is that right?
Yeah.
Yeah. So, by the way, why is Q for rational numbers?
It's like German.
No, you're thinking of integers, which is a Z. Zahn or something like that, I think, it's the German word for number.
I know why.
What?
Because the real number system is an R too.
Well, oh, that's why we use a Q for rational. That's a big reason. But also Q stands for a quotient. Well, you're 100% right. Otherwise, we would use R for rational, right? But Q is for quotient because a quotient is a ratio, a fraction. Okay? Right? So Q for rational numbers, Z for integers, N for natural. What do we use for whole? W. And that's the one I don't remember. Irrational numbers.
R with the 2. I mean,
I is irrational. And then real number is R. So make sure you're aware of those symbols that we can use to represent the natural number set and everything else. Then the integers, everything, all those. Is that where the double is supposed to be on the end, or is it on the back side?
Honestly, for the end, I'm not sure.
I don't remember either. I'll figure it out. I'll let y'all know. I'll look tonight. It's one of those two. So it's either that or this. I have to look it up. Okay. So writing domain, this is a skill we do need. Set notation. What do we need to remember for set notation?
What you talking about, the set of eggs?
Okay, so what do we use to start that set?
What do you
Curly
look?
bracket.
Curly brackets, right? So we use, that is an ugly curly bracket. I'm going to write it over here so I have plenty of room to write.
looks like mine.
So when we do set, we start out curly bracket, and remember that tells us the set of. Now, is it always going to be an X when we use set notation? No, X is just, it's just whatever variable you're using. But the next part is always the same, what comes after that X. Okay, what symbol do we use for that? Vertical line. You can also use colon, but it's a vertical line. And so that's just the set of X when so it could be whole maybe if you're dealing with what type of model.
Whole numbers.
What type of model would have whole numbers though? Continuous or discrete?
Discrete.
Right. Whole numbers, there's a lot of gaps in there, right? We don't have everything in between 0 and 1. So if it's discrete, you could use the whole number system. If it's continuous, you would use the real. Please keep your mask on. So I'm just going to put a blank here and say real number system, or number system. Yeah, because I guess we haven't really defined. There's sometimes another section that we put right here, but we'll leave that alone for now. Okay. But X is an element of some number system. Alan, did you get all that down? Under the set notation?
What you started writing? Not yet. You want me to write that part?
This part?
Yeah, you started writing off of the paper, so.
Yes, because it was hard for me to write down that. That's why I wrote set.
Oh,
though.
that's what that is. I apologize.
Yes, that's your set notation. It was just hard for me to write.
Yeah, alright.
I
That low.
apologize.
You're good.
You know those only for real number system.
Okay, what type of model are we dealing with if we're on the real number system? Which one? Yes, we only use interval notation, so only for continuous models. So what is the first part of the interval notation?
Parentheses.
Bracket,
It could be parentheses, it could be brackets, so let's explain when would you use parentheses?
when it cannot be equal.
Okay, when a value cannot be equaled,
It's in my notes. That's how I know.
so we need to study our notes. These are things we need to know.
I'm not driving now.
Okay, so use parentheses when the value can't be equaled. What comes after either that opening parentheses or opening bracket?
A number.
Which type of number?
0.
Does it have to be 0?
No.
It's a natural number. Or an integer.
Or just a minimum?
Yeah, that's a.
The interval notation always starts with a minimum. It shows you what the lowest number is. And if that minimum cannot be equaled, then use a parenthesis. Like you can never equal infinity, it's just, or negative infinity, it's never gonna happen. But you would have a minimum value.
That'd be a crazy number. If
Well-
that was possible, that would be like,
It's it's more of a concept than a number. Okay, so,
2.
say again. Okay. Does anyone know what would come after the minimum?
The maximum.
Maximum would make a lot of sense. There is one symbol that we're missing in between though.
Comma.
Why is that about the same thing?
Okay, so we always put a comma in there. Remember how an interval notation is for a continuous model?
Yeah.
Sure. Yes.
It's literally on the board.
Yeah,
was-
I
that was-
know.
Okay, so the comma is indicating that it is every number in between the minimum and the maximum.
Yeah.
Which is why it's only for continuous, because it's only on the real number system. So that comma is indicating everything between the minimum and the maximum. Now, we already talked about a parenthesis. What is the other option though?
Bracket.
A bracket, a square bracket, not a curly one, a square one. When do you use the bracket?
When something can be equaled.
Okay, so if parenthesis is when it can't be equaled, the bracket is when the value can be equaled or included is the other way to say it. Okay? So a minimum, comma, a maximum. Donovan, have you written all this down, bud? We want to struggle, this is under interval notation. We struggle on assessments, we struggle on doing homework, yet we don't take the notes to be able to help us do the homework in the assessments. It's not a smart combination. We are going to have a day of break from looking at this graphical organizer tomorrow. We will come back to it on Monday. We're not close to being done, but I just want you to be aware of that while people are finishing this up. Because I'm going to teach you how to use a resource called SymboLab, another resource called Desmos, and Khan Academy to help you when you're at home trying to do your homework. No one, after I teach you all about this, no one will have an excuse to not do homework again other than, hey, I just didn't want to do it, Mr. Kenny. And then, well, you will earn what you earn. Okay. So, what's our intern's name? Good job, Anthony. Good job, McKay. Alright, so Mr. Lipum,
Grade, isn't it?
say again?
Another homework grade, isn't it?
Yeah, that's exactly what it is. So here's our objectives, same as it's been for a while now, so I'm just going to quickly blow through them. We want to differentiate continuous from discrete. Hopefully we hit that pretty well yesterday so that you can always be able to do that. We're about to finish up talking about writing recursive and explicit equations of linear and exponential functions. We're going to talk about writing, well, we talked a little bit about writing domain already. And then we're going to hopefully get to arithmetic and geometric means today. So, recursive and explicit equations. We talked about this a little bit yesterday. How would I do a recursive equation for something that has an additive rate of change? What would a recursive equation look like?
F of n equals F of n minus 1 plus d. And F of n
Okay, so what is McKay defining here with f of a equals b? Smooth.
Done?
Yeah, really.
It was earlier than that page. It was on the first page, it was on the back. We worked on it yesterday, right there. So we're looking at those recursive equations and the explicit equations. So, additive rate of change, this is always how it's going to be set up. Okay? But what is this f of a equals b defining?
Starting point.
Okay, to write an equation, Donovan, are you taking notes? We're defining our starting point. So what is f of n equaling f of n minus 1 plus d doing? You can't hear you, Caroline.
She was speaking to herself.
Okay. Well, so it's the current output equaling the previous output. But what are we doing to the previous output?
Adding.
Adding
D.
d. And so
Okay.
that d is not my starting point, it is my rate of change. Right? So if this defines my starting point, this is defining my rate of change. What does that d stand for?
Difference.
A common difference or a constant difference, right? So the idea is that if we have an additive rate of change, we are repeatedly adding that common difference. What would it look like if it is a multiplicative rate of change? Yeah, so it is, I mean, if it's multiplicative, so f of n equals f of n minus 1 times r, the common ratio. So we're defining the rate of change here. Right? F of n equals f of n minus 1 times r. There's my rate of change. Should have changed to a different color earlier, sorry.
It's okay.
What do I still need though for this multiplicative rate of change? Starting point. Okay. Now, there's a few different ways to write explicit equations for both of these, but I'm going to give you, we're going to talk through a little bit of the most common way or the best way maybe to do this. We will get into more details with this later, but I'm going to focus on a couple details. So how would we